In this video, we'll be refreshing on experimental design, which is from Unit 3. In this experiment, we have a biologist who's examining two different brands of weed killer, brand X and brand Y, and he wants to see what effect they have on garden plants. He has 24 plants that he's going to use in an experiment to determine which of these brands is less likely to harm plants in the garden. In part A, we're asked to explain how we would carry out a completely randomized design. Anytime we're asked to design an experiment, we want to think back to the four key principles of experimental design. Those are randomization, replication, control, and blocking. Starting with blocking at the bottom here, this is optional. We only want to include it if there's a reason to include it. So let's say, for example, of these 24 individual plants, we knew that 12 were tomato plants and the other 12 were cucumber plants. In that case, we would block by type of plant, and then we would assign the treatments. There's nothing in this question that indicates blocking is necessary, so we're going to leave it out. The key thing that we can't leave out is randomization. We always have to explain pretty thoroughly how we're assigning our treatments to the subjects. Replication is just another word for repetition. We're going to do each weed killer on 12 plants. And control means eliminating external sources of variation, or really controlling them to the best that we can. So the only difference in one 12 group of plants and the other group of 12 plants is the type of weed killer that they receive. So we could write something like this: number the plants from 1 to 24. Using a random number generator, randomly select 12 of the plants, ignoring repeats, and spray them with weed killer X. The remaining plants are sprayed with weed killer Y. That's our randomization and explaining how we randomly assign subjects to treatments. Okay, this last sentence here is going to explain our response variable and how it's measured. Wait 14 days, observe the average effect scored on a scale of 1 to 10 that each weed killer has on its group of plants. If this was a question on an actual AP test, there would be a full graded point dedicated to just how you describe the randomization. So here's how I recommend you start off any question like this. We would number the subjects from 1 to n being the sample size, which in this case is 24. Randomly select the first group, in this case half of the plants, ignoring repeats to receive treatment 1, assign the remaining subjects to the other treatment, and then finish by writing something about your response variable and how it's measured. Moving on to part B, the 24 plants are located in two different areas of the garden, with half getting 8 hours of sun and the other half getting 12 hours. What changes would we make to the design? Now let's say that at lower temperatures, neither of these weed killers is particularly harmful to garden plants, but as the temperature rises, their effects on the plants increases. In this case, the amount of sunlight that the plant receives could be a confounding variable. A confounding variable is an external variable that affects our response variable. So let's say, just by chance, we randomly assign these treatments to all 24 plants, and most of our group X goes in this sunnier group of plants here. Okay, we get to the end of the experiment, we see these plants have done a lot worse. Okay, but at this point, we don't know, is it because this weed killer is worse, or is it because they got more sun? Okay, it's impossible to determine if the differences are due to the assigned treatment or due to the confounding variable. So the way we deal with this is with blocking. We want to block the plants based on their location in the garden and randomly assign treatments within each block like we previously described. This way, the 12 plants that receive weed killer X are split up, with half of them being in the shadier group, half of them being in the sunnier group. This is going to reduce variability if we were to repeat this experiment, and we get more consistent results. How could we incorporate blinding? If this was an FRQ question, we'd want to make sure we explain it in a way that shows we understand what blinding is. Something along these lines: after conducting the experiment, have an independent examiner come in to evaluate the health of the plants. This examiner would not know which weed killer was sprayed on which plant. This last sentence is key because that's showing you understand what blinding is within this experiment. Part D is just a refresher on some of the terminology involved in experimental design, asking us to identify factors, levels, treatments, experimental units, and response variable. There's one factor, that's the weed killer, at two levels, brand X, brand Y. The treatment is the combination of all factors and levels. So in this case, there's two treatments, again, weed killers X and Y. Experimental units, that's who the treatments are being assigned to. In this case, we're assigning these weed killers to the plants. And the response variable is a visual effect that the weed killer has on the plant scored between 1 and 10. So we conduct the experiment. We have our independent examiner come in and score each plant from 1 to 10 to make sure our results are blinded. Averages are obtained for each group. Which inference procedure should we use to evaluate, is there a difference in the average effect each weed killer has on the plants? So we know there's two samples because we have a sample for weed killer X and a second one for weed killer Y. Here it's telling us that we have quantitative ratings. Okay, so scoring us from 1 to 10 is a number. We can get an average from that and the standard deviation. So we're down to two things at this point. This is either a two-sample t-test or it's a paired data match pairs t-test. Okay, there's nothing linking these two groups. They're independent. So this is a two-sample t-test. A two-sample t-test is conducted. The resulting p-value is 0.9641. What conclusion do we make? We're going to fail to reject the null hypothesis since that p-value of 0.9641 is high, very high. There's insufficient evidence to suggest that there's a difference in the average effect each weed killer has on garden plants. This is just the M and the S of phantoms based on that p-value. Interpret the p-value of 0.9641. This is the statement that always begins with if the null hypothesis is true. And we haven't actually written hypotheses, so let's start with that. It's a two-sample t-test, so we want two means. And the null hypothesis is always that the difference between those means is 0. The alternative is saying, is there a difference? So difference not equal to 0. I have both of these written out verbally over here, but you don't have to do that in normal cases. It's only to assist with writing this. So we want to start off by saying if the null hypothesis is true and the mean effect of the plants on the plants is the same, then we're down here at this point, the probability of seeing a difference as large or larger than the one seen in this experiment is 0.9641. Okay, so there's a 96.4% chance that if this is true, we would see the results that we saw or more extreme than that. So what that's telling us really is that when we rated all the plants that were sprayed with weed killer X, we got an average that was really close, let's say 8.3, to what we got when we rated all the plants with weed killer Y. Okay, so they were so similar that our results are showing this would happen pretty much all the time. That difference isn't unusual at all.